Okay.
Hello, good evening, everybody. It's a pleasure to introduce to you tonight our guest speaker. Is Roger Deane. He's currently the professor and director at the Centre for Astrophysics at the University of the Witwatersrand. I stumbled upon his name and became aware that he was part of the international team that obtained the first image of the black hole at the center of the Milky Way using the Event Horizon Telescope. And therefore, I think it's appropriate that his main topic tonight will also focus on that. And we're looking forward to his presentation tonight. Thank you very much, Roger, and over to you.
Great, thank you very much for that kind introduction and the invitation. It's great to be with you all remotely, but I far prefer visiting Amanus in person. As I was mentioning to Derek, I'm there about once a year with my parents-in-law, and I'm very envious of where you live in the world. It's a beautiful, beautiful place. So hopefully in the future I get to have another go at this in person. Yeah, so I was asked to talk about Sagittarius A star. So this is the supermassive black hole at the center of our galaxy. And let me bring up an image of that cover slide. And you may recall from earlier this year, it was in May, there was an announcement of the first image in the center of the black hole. Sorry, this is going wrong. The center of our galaxy, called Sagittarius A star, using a slew of telescopes. And there's a bit of a montage. This isn't one geographical place, but it tries to represent, as you'll see later on in this presentation, some of the huge range of different powerful antennae spread across the Earth that are used to observe and create this image at the center of our galaxy. So I'll try and take you through beyond the newspaper headlines and sensationalism, and just a little bit more into how this actually works and how we, as a global team, do this together. Right. So it really is a massive team of diverse expertise spread across 80 institutions on 5 continents. There are only 2 of us on the African continent. Sadly, now only one, actually. My postdoctoral fellow, Dr. Inian Natarayan, over here on the front, has just been poached by Harvard. So I'm going to have to be doing a recruitment drive. So if you know any young budding astrophysicists who are interested in black hole science, let me know. But yeah, over 300 of us part of this huge effort. This was our collaboration meeting just before the first announcement, 2018. Like everyone, we had to do things remotely for a number of years during the pandemic. We just had our first in-person meeting back in June at Granada in Spain. Unfortunately, I couldn't go because I couldn't get a visa in time. But yeah, it's been incredible working with this team. Just a huge range of expertise and backgrounds and experience. Yeah. So they're spread across, the actual people are spread across these sites around the world. These are the different institutions. And I'll show you where the telescopes are in a moment, but truly a global effort. This won't be as relevant, but this is the board. It's 13 main stakeholder institutions, some of the biggest institutions in the world, Harvard, MIT. It's an expensive exercise, and these 13 institutions foot much of the bill. It's actually to keep these telescopes running. But it's broader than that. It's human expertise as well. And these are some of the affiliated institutions. So you can see the University of Pretoria here, and here's Wits University and Rhodes University. Those basically are my own affiliations and my postdoctoral fellow. And then we receive funding from the National Research Foundation through the South African Radio Astronomy Observatory. So I'll tell you a little bit about what it is that we actually imaged. What is this black hole shadow thing that we keep talking about? Then tell you a little bit about the instrument and how it achieves that. And then dive into a little bit more detail on these first results of our galactic center. And then a major project that I'm part of now is as you'll see over the course of the presentation, we really need to expand this array to enhance our test of general relativity. So in order to do that, a key strategic place to go is actually putting additional telescopes towards in the southern region of Africa. And I'll close with that. But let me start with the primary science goal. When the Event Horizon Telescope collaboration was put together, its primary goal and everything that was deemed to be on the critical path was towards this goal of imaging the shadow of a black hole. So what is a black hole shadow, you might ask? Well, there's a very old view graph here. I think this was made, I won't even venture a guess, I've forgotten. But think of this as you've got a side view of, this is a white object, but it's a black hole or a very dense object bending or curving the local space-time. And what you have orbiting around a black hole is a thin disk of very hot plasma. So that's the red. You're seeing it cut through the red there. That's emitting photons, but those photons are following curved paths, well, at least to us, in the curved local space-time. So if you were to look at this thin disk, think of Saturn's ring that's cut in half here, or slice through them, from this direction, you essentially see the light from the front of the disk, and I've got some animations coming up that's going to explain this better, but you're seeing light from the front of the disk here, but light curves over the black hole and under the black hole, so you actually see two images at the back of the ring. Think of it that way. And that's what this is. And that casts, if this accretion disk, or if this red thing is close enough, it actually casts a so-called shadow. So there are two key concepts in understanding this, and this animation that's coming up now should hopefully drive it home. But you've got this light bending around the black hole, but then another key aspect to this is light photons being captured by the black hole, passing the event horizon. And that causes this deficit of light, which we call a shadow. So here we have photons traveling in the immediate vicinity. When they get very close, they bend. Some of them get so close that they start to orbit around the black hole. And what you have is some of them actually disappearing into the black hole. So if you look at that from a distance, well, you see an enhancement of light around the perimeter of the so-called shadow. You see a deficit because some of the photons are being captured by the event horizon. And so this feature is basically called the black hole shadow, and this is the M87 black hole shadow we captured and released back in 2019. I won't show too many equations tonight, but just to give you a sense that it's actually, the point here is just to emphasize how small the shadow is. So with the photon ring diameter, at the size it appears on the sky, is square root of 27 times Newton's constant, so 6.67 times 10 to the minus 11, very small number, times the mass of the black hole, divided by a very large number squared, speed of light squared, also divided by the distance to the black hole. So without really paying too much attention, I think you can immediately see that this is an exceedingly small quantity. And the mass really dominates. So this is for a short-trailed metric, a non-spinning black hole. But if you start spinning it, you don't really change this diameter by much, which is fortunate for robustly testing its mass, but it's unfortunate because it's really hard to actually measure the spin of the black hole using this method. And it's one of the reasons we want to try and improve our imaging. Now, a complication to this very simple formula is that you've got some very messy astrophysics, as you guys will well know, in the vicinity of a supermassive black hole. So here we have what's known as the accretion flow in red. You've got hot material swirling into and heating up, swirling into the black hole. Some of us get launched because you have twisted magnetic fields here, launching particles in a bipolar direction, and there may or may not be jets. But right in the center there is the shadow feature that we're talking about. And obviously there's a whole lot of, complex thermodynamics that's happening here, which complicates getting out a very clean shadow-like feature and comparing that with what we expect. But nonetheless, this is what we simulate and what we see. So there's a still from that simulation done by a colleague of mine, part of the Event Horizon Telescope. He was a PhD student at the time. And you can see if you dive in there, well, that is that shadow-like feature. And in the case of M87, the black hole that is 6.5 billion times the mass of the sun that was captured in 2019, that engulfs the entire solar system, at least its apparent size. And it's that which we zoom in on, that innermost feature where you've got the hottest possible gas. There is a jet coming out in that case, but we don't see that in the event horizon telescope, and I'll talk a little bit more about why that is. So you've got an event horizon through which nothing can come back once it's passed. But then you've got a so-called photon ring, this enhancement of light, and a deficit within that is bent around the black hole. So it appears what we call gravitationally lensed, but it's larger than it would appear, a bit like things appear larger through a water droplet on a pane of glass. There are some predictions way back in 2000, and in fact earlier than that, but the co-chair of our science council, Heine Felker, made these predictions back in 2000 and made the prediction that you could use this technique to actually see this. So he made some simple models back in 2000 about how hot the gas would be, the composition, the mass of the black hole, the spinning, and made a prediction as to what this feature might look like. And it's remarkably similar, to first order. Okay, so that's black hole shadow in a nutshell. Let me go into the Event Horizon Telescope and how it actually tries to capture images, is designed to capture images. So the first thing to note is that these sites are at extreme locations and they're spread across the Earth. So here you can see this is in Hawaii, the submillimeter telescope. This is in the Andes at 5,000 meters, and this is at the South Pole. That is the South Pole telescope. And you really need these to be up at the extreme altitudes to get as close to space as possible, but you also need them spread very far apart. And I'll go through that in the next few slides as to why those two facts, the constraints are there. So the first is that the EHT, or a radio interferometer or an interferometer, is not a digital camera in any sense. It's not a point and shoot device, alas. You actually need to capture voltages of individual antennas. So this is a very, very well-known interferometer, radio interferometer in New Mexico in the US. South Africans would say it's now the second best radio interferometer on the planet, second to MeerKAT. But nonetheless, the way to think about this is not as a, well, one way to think about this is not as a single telescope, but as pairs of baselines. We'll think of each pair of antennas having I think of it as a handshake. It might be a handshake every few nanoseconds, split across 32,000 frequencies, but it's a handshake nonetheless, because you're basically comparing the electric field above this antenna to this antenna, and it makes this baseline, what's called this pair of antennas, which makes a baseline, makes a single measurement per unit time, per unit frequency. And you combine a whole lot of these together to then synthesize an image. You don't take an image as you do with a digital camera. So we call this, well, what this is actually doing is measuring something called the Fourier transform of the sky. But I won't go into too much detail about that. There might be something in the Q&A for people who've covered that in the past. But the number of handshakes that are happening obviously goes up almost as n squared, where n is the number of antennas. So for this interferometer, there are 27 antennas. So there are 351 of these handshakes happening every unit, per unit time, per unit frequency. MeerKAT, that goes up by almost an order of magnitude to 2,000. For the SKA 1 mid, will be of order 20,000, and then up to 3.1 million if we build the full SKA. Now, the key thing is the EHT is very few of these antennas. We've only got 28 back in 2017. So that makes our life very, very difficult for creating high quality, high definition imaging. Another key aspect here is that the further these antennas are apart, the sharper the detail that you can actually see. And that's why the EHT has its antennas spread across the Earth. You're trying to synthesize the the highest possible resolution you can achieve on Earth. So just in a nutshell, for the people that maybe have dealt with Fourier transforms in the past, this is a building at the University of Pretoria. You can see some periodic features here in the different stories. You can also see a large scale, there's dark on the side, dark here, and then bright in the center. And what you can see is this is a so-called 2D Fourier transform, just think of it as a mathematical transform that captures encodes some of the information that's in this image. And if you have a perfect image, well, you can have a perfect 2D Fourier transform. But what we do with our interferometers is it's a bit like a broken mirror, and we're only capturing parts of the information. So here, I've just cut out a few annually of this image. But even with that, I can still create, some of the salient features of this building, even though I've blanked out much of the information. That's basically what interferometers do. But the more antennas we have, the more we fill in, the more information we capture of the perfect Fourier transform, and the more we're able to capture what's going on. So an example of that is, as the Earth rotates, here's a pair of antennas, a baseline, and each of them makes a measurement in this abstract mathematical plane. And the more these measurements you have, the better you can actually make the image of the black hole shadow. More shards of glass in a broken mirror, if you will. All right, so these few shards of glass that we have on the planet need to be in special locations. They need to be very high up on high mountains. I said that's because they need to be as close to space as possible, and because they weigh thousands of tons, they're very expensive to put in space. So you go high. You go high because you're trying to get over the atmosphere. Basically, any precipitable water vapor you have in the atmosphere absorbs the radiation at which the EHT observes very, very efficiently. So the SKA observes at wavelengths of order tens of centimeters to a meter. The EHT is at about 1,000 times shorter wavelengths, so about a millimeter. And here, what is plotted here is atmospheric capacity. And basically, where this line is 100%, none of the light coming from space is penetrating through the atmosphere. And that's effectively true for 1 millimeter wavelength, unless you go to high mountains. If you go to high mountains, then some of this light does penetrate through, and you're able to do this wonderful science that the Event Horizon Telescope does. We have very few antennas, but we still got a big data problem. We have to capture a lot of this, a ton of data, of order 4 petabytes, the EHT 2017 and a run. That's quadrupled already for this year's run, and will continue to double as we increase our bandwidth. And essentially, the reason we have such large data sets is we can't average until we bring it all together at one central supercomputer. And that's done in Bonn in Germany, as well as MIT in the US. So we have to store the data at extremely high time resolution, or very fine sampling of the data, and only then can we bring them together. Can we synthesize those baselines where you actually cross multiply voltage streams from each possible pair of antennas. And this is the disks that are arrived at MIT, I think back in 2017. Now what's weird is you start with 4 petabytes and you end with an image that's literally a few kilobytes, because you see it's just that ring. We don't have a lot of other information. We've only really got the information in the immediate vicinity of that ring. So it can be a little bit deflating. What people don't realize is that South Africa has already contributed to the Event Horizon Telescope. The SKA effort produced these so-called Roach boards. It's a digital backend that does a conversion from analog to digital, and it does some filtering, which is at the base of every EHT station across the world. You can see the globe here showing the different stations. And at each one of those is 4 of these boards, and that's going to increase now, which is South African technology. South Africa led this campaign. So essentially what happens is you've got these antennas spread across the Earth. You record onto those large disks. You then put them on an airplane. In the South Pole case, you wait for winter to end. Then you put it on an airplane. You take them to a central supercomputer called the correlator, and then you sync them up. You've got to do the timing and make sure that those, when which sample gets multiplied with which is done at the exact right time. And it's kind of what we loosely call the calibration and fringe finding process. And once we've lined these all up and done some fine tuning, we can eventually create an image. So in a nutshell, you're using something like this Earth-sized telescope that's spinning. It's critical that it's spinning because you get a whole range of different baselines coming into play, and you're trying to image the swirling hot gas. Some of it is being captured by the black hole. Some of it is the light is actually orbiting around, but you're trying to use this to get that, capture an image of that sort of dark ring-like feature that is the apparent size of a donut on the moon in both the case of the 2019 result and the result announced earlier this year. They're both about the same size. Okay, so where do we go and look for these black hole shadows? Well, our two primary targets are black holes that lie at the heart of two very different galaxies. One is a spiral galaxy that we actually live inside. So this is a model of the Milky Way using the best data we have. And we live about 2/3 of the way out there. You probably can't see it here, but that's the Earth. And the black hole is 27,000 light years away. It's right in the heart of the Milky Way here. So if you look up at the night sky and you see that band of the Milky Way, and it's roughly July, well, it'll be, you guys know very well, right up ahead there in Sagittarius. The other target is M87, which is about 55 million light years away. Elliptical galaxy, about 1,000 times more massive a galaxy than our galaxy, and the black hole as well is about 1,000 times more massive, 6.5 billion times the mass of the sun. Okay, so this is a little promotional video that shows the process of this campaign to shift to image the second black hole image, but the one that's center of our galaxy, which is harder for a number of reasons. And I'll just let this video play. The sound is not so important. I'll just take you through. So I showed you that we're about 2/3 of the way out in the Milky Way, something you probably know very well. We live in this plane. So we're using these antennas spread across the Earth. They've got to be as far apart as possible to be able to see the finest detail possible to actually make out the shadow. And they're at these extreme sites. So we're going to dive into Hawaii here, and more specifically, a volcano in the Hawaiian Islands at 5,000 meters. It's Mauna Kea. This is the submillimeter telescope pointing at our Milky Way center. You see this beautiful MeerKAT image that was taken and released earlier this year. And then you may remember the Nobel Prize back in 2020 awarded for these stars orbiting this dark object, about 4 million times the mass of the sun. And then if you zoom in even further, this is the image that was captured and announced earlier this year. So that is a 4 million solar mass black hole bending that plasma that I was speaking about and creating the shadow-like feature captured by the Event Horizon Telescope. So we had a little press event in the Wits Planetarium earlier this year, which was quite a lot of fun. Hard to remember a time when we were still wearing masks. That wasn't that long ago. Incidentally, we're upgrading this Zeiss projector. Some of you might be interested. This is, well, the planetarium is 62 years old, but there are parts of the Zeiss projector that are 91 years old. It used to live in the Hamburg Planetarium that I was privileged to visit just 4 weeks ago. And it was moved here in the late 50s. But we're retiring this and we're upgrading this to a fully digital system. So we look forward to you visiting us at some point once the system's installed next year. So let me tell you a little bit about this shadow image. So you're probably used to dealing in seeing of order an arc second and that kind of resolution. Well, this is an image of a ring-like feature that is 51.8 plus or minus 2.3 micro arc seconds, so a millionth of an arc second. So a donut on the size of apparent size of the donut on the moon is basically this. You can see that it's not as clean an image as the M87 black hole image was back in 2019, and there are several reasons for that. One is that we're actually peering through the gas that's in our Milky Way plane. And more specifically, between us and the black hole are a lot of free electrons. And what the free electrons do is actually scatter the light from this black hole. As they scatter, think of a hot road in the Karoo as you're traveling along, and you see that mirage-like feature. There's a similar kind of scattering effect happening here, analogous at least. And that's blurring out some of the light. But the other thing that's happening is the accretion flow, the plasma that's swirling around, is actually doing so on orbital timescales of order minutes. So while we're taking this long exposure photograph, think of it that way, over the timescale of 12 hours, you've got this gas orbiting many, many, many times. So these three features may be enhancements from one period in that, or they might be accentuated by our lack of enough shards of glass to create a perfect image. But what's clear is that there is no matter what we do, there's a deficit of light towards the center and an enhancement of light, a ring-like feature. And one of the key things to do is to now repeat this experiment over time, and more specifically to add more antennas so that we can improve the snapshot capability and actually make movies of this black hole. At the moment, we don't have enough antennas to actually capture that movie. It's just moving too fast for how many we have. So what this image does is show you that there isn't just one image of the black hole center of a galaxy. That would be like saying there is one image of my 4-year-old during a long exposure photograph of 3 minutes. He would definitely be running around during that 3 minutes. But so what we've done is had a look at the different classes, and you can see it falls into different classes. And the histogram here gives you a sense of the distribution of those different classes. And these three here which are the majority, are very ring-like. And then there are images that just don't look like anything. Well, don't look like a ring. This is the challenge we face, and why we need to build more antennas. But what we do build into the EHT is redundancy. So we use this is definitely, I think, it's been claimed to be the most vetted radio interferometry image of all time. It's hard to state that and verify that, but it must be amongst the 4 different imaging algorithms. There's what we call visibility analysis, Bayesian analysis on this. We see the similar kinds of image on 2 separate imaging days, and if we split up the data, we see similar images. So, yeah, it's a pretty robust result, and also been confirmed by independent teams. Now you can see now M87, the 6.5 billion solar mass black hole. This is the same approximate size in the sky relative to Sagittarius star. You can see this is just a little bit bigger, and you can see not as neat as our M87 friend over here. But this black hole is about 1,000 times less massive, as I said. So if you had to put them on the same scale, you would see that, you saw this earlier, M87's black hole can fit the entire solar system inside, whereas the Sagittarius star, our Milky Way black hole, would fit inside of Mercury's orbit. So they're very different beasts, but you're seeing a very similar kind of feature, which is, to us at least, a remarkable confirmation of predictions of Einstein's general theory of relativity. I mean, black holes are, they're objects that don't scale, they just scale with mass, right? So you should be seeing similar features, and that's indeed what we see. And both are consistent with the predictions we had from the masses that we measured. So yeah, I said that this image on the right was harder than the one on the left, and the reasons are this: it's 1,000 times more rapidly varying. So, you know, long exposure photographs of toddlers versus, you know, the dignified, stately portrait that's being taken here of a much larger beast. And then it was, as I mentioned, the free electrons that we have to look through the center of our Milky Way in capturing this image, which scatter the light. It's a complex environment. This is another color scale version of that beautiful MeerKAT image produced by Ian Hayward. And the black hole lies right at the center of here, but you can see a lot going on in this environment, which is part of the complexity. There's a lot of large scale emission. This is a supernova remnant. There's another supernova remnant. There are these filaments that were known, but MeerKAT has, I think, increased the number of them that have been robustly captured by well more than an order of magnitude. And yeah, it's a very interesting place. Another reason, well, just to kind of illustrate the challenge of this rapidly varying black hole, if you zoom out from EHD wavelengths, and if you actually use a telescope called ALMA at the same wavelength of light as that we observe the black hole, but with baselines that are 100 times shorter, you see this point-like emission, very, very bright region, and then you see this sort of what we call the mini spiral. And if you plot the light curve of this, the intensity of light is a function of time, which you're going to see here from 4 hours to 14 hours, you can just see that this is so rapidly varying. This is the actual data. Decreases and then increases. And this is one of our biggest challenges. Even if it's a point source, even if you don't have complex structure, the fact that it varies so rapidly makes it very, very difficult to calibrate the data, to correct the data, to line up voltages, and make sure that we can make this robust image. I won't go into too much detail, but the image is not a means to an end. It then needs to be compared to theoretical models. That's how you're not just testing whether this is consistent with Einstein's general theory of relativity, but you're also testing some of the thermodynamics in the immediate vicinity of black holes. This is not an area that I'm an expert, but a huge number of my Event Horizon Telescope colleagues are. And they're able to test remarkable things about the magnetic field structure in the immediate vicinity of black holes, and the jet launch capability. So what you're seeing here, these spirals are different models of different magnetic field configurations. But you're not done there. You can simulate this, but if you're actually observing this, remember that light bending that's happening around the black hole. So you have to take these very complex models and then create a library of shadows in order to compare with the image, the data that we actually captured, in order to constrain different models and what's the most consistent. So it was a huge theoretical effort from a very large number of gifted theorists around the world, using supercomputers to basically produce this library and then slowly remove those black hole models that are not consistent with the data. And they compare a whole range of different things. So there's some really spectacular work. What's also interesting is you can't just compare those perfect images. I mean, this is very different to the blurry donut that you've seen. So part of my contribution and my postdoc is to actually go from, okay, well, we've got a perfect theoretical image. What does that actually look like through the optics of our telescope? And that turns out to be a slightly more challenging problem than one might want and first anticipate. So we built a whole software pipeline to basically mimic our instrument. And yeah, Dr. Ryan was a key player here. I'll skip through some of this. This is just to show that we measure different parameters of the black hole, and we use a whole range of different techniques to calibrate our data and image our data. And we see very similar results for a lot of the parameters. We're also able to compare with different models of black holes, not just assuming general relativity. We need to improve our images to really to do better here. But at the moment, there are some extreme variants, like a boson star that are pretty ruled out. I think I should just close in the final few minutes on talking about the future. something called the next generation EHT. As I've mentioned several times, we really are looking to expand the array in order to improve the imaging. And what you can see here are in cyan are a number of proposed sites to join. One is in Namibia. We're also leading the charge to have a smaller antenna here in South Africa, in South African borders. Part of the rationale there is we have really good infrastructure at a number of sites. So if you put in a telescope where there is existing infrastructure, it can cut the costs in at least half for something like this, if not more. And so you can see we're putting more and more shards of glass on the planet in order to improve the imaging. And an example, a simulated example of that is here you've got the perfect image. Here's what you would recreate from that simulation back with our 2017 array. And if you assembled this array, then you would capture this kind of, you achieve this kind of fidelity, which you can see is a much sharper shadow, but also you're able to capture this larger scale jet base and tie the black hole launching to the larger scale base. We also do polarimetry, and the polarimetry is the prospects are extremely good with the enhanced Event Horizon Telescope, as well as the snapshot capability, being able to see hotspots of plasma orbiting around Sagittarius A star on the time scale of minutes. This is in units of hours, and you can see there is the truth image here shows this hotspot of plasma orbiting around the black hole, and what one can capture that from 2017 versus the NGHT to come. So yes, there's lots of interesting science to be done with this. It dovetails very nicely with a square kilometre array from a scientific perspective, testing gravity, understanding jet launch from black holes, but also there is a good geographic advantage that can piggyback on the square kilometre array as it expands across the African continent. You can see these stations are nowhere near Africa, and there's a big gap here, and especially for the galactic center, which lies right above us here in Southern Africa. If we want to make these kinds of movies, we really need to put stations on the African continent, because as you can see with the spinning globe, we're looking at the Earth from the vantage point of Sagittarius A star. And so you can see how critical southern stations are here. And if you put a few stations on the African continent, you're able to link up to Europe and South America and parts of North America. So to be capturing this, which you can see changing on the timescale of minutes, this hot plasma orbiting around Sagittarius A star, you really do need to enhance the array. We just can't do this yet. And this is really just a unique gravitational laboratory. So we're working on that. These are some simulations we did to enhance this. I've spoken about its synergy with the Square Kilometre Array, which is a different talk to be done at a different time. But yeah, we're really excited about this. Making these Earth-sized telescopes is not just something that we're doing at the Event Horizon Telescope, but the Square Kilometre Array itself will forge as a node within an Earth-sized telescope as well, observing at a different frequency, but the same technique. All right, so I'll close there, but yeah, I mean, I said our mission critical objectives were to image the black holes of M87 and Sagittarius A star, and in its first 5 years, the collaboration has achieved that, and a lot more, I would say, thanks to some very, very talented young students and postdocs, as well as a number of remarkably experienced and dedicated people that have been working towards achieving and assembling the Event Horizon Telescope over a timescale of 3 decades. Really impressive odysseys for a number of people in the collaboration. It's a huge amount of engineering and algorithm development, which has really pushed the field forward, I would say. A huge benefit to the community in this art of what's so-called very long baseline interferometry. The black hole masses that have been measured are consistent with general relativity and also consistent with what's been measured using other techniques, one of which is a Nobel Prize winning method. But really to go deeper than that, we really need to expand the array, and I've convinced you that Africa is a key part of that in order to make these movies and able to do these general relativistic tests on the timescale of minutes rather than hours. So that is it, and I look forward to your questions. Thank you.
Thanks very much, Roger. That was really fascinating. I don't know if I can maybe just kick off with a question. Are there any of these space telescopes which are suitable for including in this Event Horizon Telescope at all? Are there none?
Not at the moment. Not at the moment. There is actually a radio interferometer station that is in orbit, but it doesn't observe at a high enough frequency to participate in the Event Horizon Telescope. But plans are afoot. In fact, there's a meeting, a conference happening just this week in the Netherlands on planning a station that can orbit and participate in with these stations that I presented today. And then a second mission concept is to have 3 to 4 stations that don't connect with these ground-based antennas, but actually just are all the same spacecraft design, same optics, and they just operate as a single telescope, all of their stations being in orbit. And there are a number of advantages to that, data transfer being one. But yeah, this is on a much longer time scale. I mean, as you know, space missions are just, you're looking at 20 years in the future.
Talk to Elon, you get it done in a hurry. What about something on the moon? Is that just a pie in the sky or not?
I mean, this is definitely exactly where the collaboration and broadly the community would like to go. It's just expensive.
Yeah.
But there are huge scientific advantages to getting that length of baseline. I mean, 384,000 kilometers allows you to do some completely unique experiments. One of the things I didn't go into is I spoke about the ring, but there are actually multiple rings that are inside of that initial ring. And even with a single baseline, you can do well, at least theorists tell us, you can do some very, very interesting experiments. You won't be forming an image, but the so-called fringe pattern for those very, very long baselines of tens to hundreds of thousands of kilometers are very, very science rich. So yeah, also something for the future.
And the scale of the difference in those two black holes that we imaged is quite fascinating. One's like a flea compared to an elephant. And Mike talk about micro arc seconds. It's incredible. It's unbelievable. Okay, anybody else got questions for Roger? Pierre?
Can I just ask, if you had more satellites, telescopes, and you can improve the images, are you going to learn something fundamentally different about black holes, or are you just improving the images?
Yeah, so at the moment we measure the mass quite well. The mass dominates the ring size and shape, but you can see it's quite blurry. And we have this rich array. I showed you one slide just showing the rich array of black hole library, the library of black hole shadows. But basically, they all get blurred out. The majority of them get blurred out with the current imaging quality. So as soon as we're able to improve the imaging, and it doesn't take much, we're able to start putting constraints on the spin of the black hole and its orientation. We're able to put constraints on how exactly the magnetic fields are orientated, and therefore how particles are accelerated in the immediate vicinity of the black hole. We're able to monitor those what have been observed. I mean, this is known, we just haven't imaged them. Blobs of plasma that are orbiting and sort of getting ripped up by the black hole in the final throes, which are interesting tests in their own right. And then also we're able to expand this to beyond just these shadows. So these are premier laboratories, but as you make this a more sensitive and higher imaging, a higher fidelity instrument, you're actually able to apply this to many other science questions. And one of the reasons I got into the Event Horizon Telescope collaboration is I was interested in finding and still am, binary supermassive black holes. So when it's a prediction that these black holes shouldn't be isolated for their entire life. They should have a pair at some point and spiral in and generate gravitational waves. So we'll be able to enhance things dramatically for these ring-like images and the science that we're able to extract, but we're able to do a whole lot of really rich science on a wide variety of objects, far beyond just this.
Okay, Peter, so yeah, can I ask Roger, what is the maximum? Is there any theoretical limit on the mass of a black hole, or how does the size of our black hole in the Sagittarius compare to other black holes? Is it a mini size, the mid size, or how does it fit into the spectrum of black holes that have been observed so far?
Yeah, so I'll start with the second question. I refer to supermassive black holes. We have very creative names for black holes, astronomers, as you probably know. We have stellar mass black holes, which are typically, they form at the end of a star's lifetime. Type 1a goes off, massive enough that it blows up and forms a black hole of order 10 times the mass of the sun. But then in a completely different class, found in the center of galaxies, are black holes that range from about a million, let's say 100,000 times the mass of the sun, all the way up to 10 billion times the mass of the sun. So, like with many things to do with humans and where we live, it's sort of we're fairly average. So 4 million times the mass of the sun is the mass of our black hole, and that falls pretty much in the average, just like the Milky Way galaxy. In fact, it's roughly an average sized galaxy, and that's by no coincidence that they're both average, because black holes and their host galaxies tend to be correlated in their masses. Now, the other black hole, M87, is a beast. That's it's at the extreme of what we've measured. But that goes to your first question: is there a theoretical limit? If you believe general relativity, there's no reason you couldn't shove all the mass in the universe into one black hole if you could actually get it to one location, of course. There will be no fundamental limit at all. But what does limit these things is how much mass they can guzzle up over their lifetime. So, we have the birth of the universe through the Big Bang. The first stars and galaxies form, and soon thereafter the first black holes. But they've actually got to swallow up a lot of fuel very, very rapidly to get to the masses that they do get to. It's actually still a puzzle right now to understand how some black holes that we measure 1 billion years after the Big Bang are as massive as they are. We can't understand through theoretical models in hand how they can actually grow this quickly. So they grow by just swallowing up swirling gas, but they also grow by merging with other black holes. That can be a more rapid way of doing things. But in principle, if general relativity is right, there's no limit to what that could be. Yeah.
Thank you very much.
Roger, 2 questions. The first one is very simple. Have you identified your next target? But I think the more important question, first of all, thank you very much. It was an absolutely fascinating talk. You identified 3 focus areas for the future. The one is obviously to try and expand the number of participating telescopes. And then the other 2 more theoretical activities is data reduction or image reproduction, and then theoretical modeling. What is the sort of percentage breakdown of energy invested in the future in these different fields?
That's an interesting question. So on your first question, I've identified these as our 2 primary targets, but it hasn't actually been our only targets. We have to observe something called what we call calibrator sources. These are sources that are their structure is better known, and we're able to use them to check the quality of our data. But they're interesting sources in their own right, and also they hadn't been observed with an array like this at this angular resolution before. So there are a number of results that are already coming out and will still come out on other black holes that don't have the right combination of being close enough and massive enough that we can see their shadows, but we can still see very interesting phenomena in the immediate vicinity. One of them is a well-known source that many in the audience might know, Centaurus A in the southern sky. And there was just an incredible image, completely unexpected, sort of almost X-shaped in a ring. That was published in Nature Astronomy last year, led by a PhD student from Germany. Really, really impressive work. So another example is a binary supermassive black hole candidate called OJ287. So there are a number of targets, but we really want to expand that portfolio of science. But to do that, we have to expand the array. For your second question, that's an interesting one. How do we split things up? The theoretical work, my colleagues are in the EHG collaboration streets ahead, and there's a very large community. Things are really well established on how you do this, and there's just a lot of human resources behind the effort. So they very early on put together this huge library, which was an enormous effort, requiring, I forget how many millions of years of CPU hours on supercomputers spread across the earth. But they've done an extraordinary job. I think what lags behind, and similarly on the imaging inversion, and actually creating images from the raw data. There was a huge effort in that very early on, because the better you could do that, the better the science you could do right off the bat. That becomes, I mean, it'll always be important, but things get a lot more forgiving as you focus on the third of the things that you mentioned was expanding the number of antennas that participate across the array. The more antennas the more complete your information, the more measurements that you're making with more antennas, the less, I should be careful with my words, but the less care you need to put into your imaging algorithms almost, because there's a lot less freedom in the calibration and imaging process. It just, with higher fidelity imaging, it's just a lot easier to recreate this. But there we're lagging. We're lagging on a technology front and on an infrastructure front. It's very expensive to set these sites up if they're greenfield sites, but you essentially have to establish greenfield sites for most of the planet, because that's where it's important where the new antennas is. You want to be measuring orientations and baseline lengths that are different to what you already have. It's not that there's no point in measuring the same antenna, the same baseline, but it's not as impactful. You want unique measurements that are coming in. So establishing new sites is really expensive, and that's why that's what they're doing in Namibia. And yeah, it'll be a hefty bill will be part of just the infrastructure establishment. So what I'm exploring with several colleagues here in South Africa is looking at a site where we say, okay, well, let's go for a smaller antenna, let's spend less on the antenna, and let's go for an established site where, you know, we can just plug in the instrument. It might not be as high a site, and it might not be as quality a site, but if you can do it for, you know, a quarter of the price, that may be impactful. So that's what we're exploring at the moment, both in software and obviously from a funding perspective. And it's an alternative approach, and we'll see what comes of it. But one thing is clear: Southern Africa has a huge geographic advantage for offering unique measurements and really adding unique value to the future next generation Event Horizon telescope.
Thank you.
Okay, Roger, can I just ask another general question about black holes? Those two that were imaged, the difference in scale, what is the difference in density of the two? If I've got it right, I think the much bigger one is actually much less dense, just by virtue of the Schwarzschild sort of formula. Is that right, or is that wrong?
Yeah. No, that's exactly right. Yeah, that's that weird scaling of the black hole. How scales with volume. The other weird artifact of that calculation that you've just done is that if you actually pass through the event horizon telescope of the larger one, you wouldn't really notice a thing. Whereas with Sagittarius A star, or at least a stellar mass black hole, you'd get ripped apart or spaghettified. So another important reason to do your calculations before diving into a black hole.
And we've watched videos by astronomers, I think, before of this question. Is the universe inside a black hole? If you do the Schwarzschild sort of calculation for the whole universe, I think there's not enough mass in the observable volume of the universe to make it a black hole. But if you went a bit wider, I mean, the consensus was because it's space. I don't know, I can't remember the exact reasons, but they said no, it can't be a black hole. What have you got a view on that?
I haven't done that calculation. I don't have a strong view on that. No.
I think the mass of the universe is about less than half of what needs to be for it to be a black hole for the observable volume. But if you went a bit bigger, it would be because the density requirement is much less. It actually could be theoretically, but then
Okay.
there's scientific reasons why it's not true, but apparently, which I don't quite understand.
Yeah, I haven't done that calculation or read about that, so I won't be able to comment on the fly.
Just a left field question there. Sorry.
No, don't worry. Interesting.
You I think one of the slides there you had on the alternate pictures a wormhole that sort of going the other extreme of multiverses and what happens through that. Is there more enlightenment coming through that you expect, or you don't really aim for that? You just wait until you get the results before you hypothesize?
Yeah, there is a wormhole in there. This is really not my domain, and our data are nowhere near good enough to rule out many of these things. And a lot of these things are not really, the criticism of them is they're not all grounded in physics. They're grounded in, at least some theorists will say they're grounded in kind of speculation rather than physics. But there are some things that, it certainly could be. And some of these predictions are, that there wouldn't be an event horizon. There would be a surface, and there would be material slamming into a surface, and it would have to heat up, and it would shine. It wouldn't disappear, and it would, and you wouldn't have a deficit of light. So for those kinds of models, like the boson star, they're very clear predictions about what they would look like, what the albedo would be, and you can compare that with our data, and they're just a surface is excluded by our data unless it's got a very, very low albedo. So yeah, I think expanding on that will be possible with higher quality data. But already there are some models that are being ruled out.
Can I ask you a grade 1 question? In my early days, we used to use Fourier transforms to analyze the signal components of a signal, the frequency components of a signal. Now, in this case, do you use the Fourier transform to measure the periodicity in the images? Is that what it's basically used for?
We could do that, but what we do by capturing what we call baseline data. So we have two antennas that are looking towards a target. We're measuring the voltages, the electric field above both of those antennas. We line up the signals, and then we cross-correlate the signals. And what we have then is the Fourier transform, a sample of the Fourier transform of the sky brightness distribution. So we actually capture the Fourier transform, and we have to or inverse Fourier transform it to get back into the image plane. It's not that you're measuring periodicity in time, but what you've actually used there is a bit like, JPEG image can be, you can decompose any image into, a sum of sinusoidal components. And so with interferometry, we're basically capturing one sample of a sinusoidal component of the image. And if we put lots of them together, we're able to recreate the image. So it's thinking this in spatial frequencies rather than frequencies corresponding to the time domain. I hope that makes some sense.
That doesn't sound like a grade A question to me.
Well, even on a very simple level, I mean, a JPEG image of a picture is almost the same concept, just very simple.
Yeah, exactly. So what we're doing here is we're measuring the intensity and the phase of one wave, and that wave has a geometry set by the separation of the antennas. So what we try and do is measure many of those. And we do that by having lots of antennas, so we have lots of baselines. But we also observe, as the Earth rotates, something called aperture synthesis. And as it rotates, you change the orientation and the projected length of those baseline pairs. And in doing so, you get more information to make a more robust image.
Can you use fractals in your imaging?
You have to make some assumptions about the smallest scale that you can't capture. I remember I said the longest baseline basically determines the smallest, the finest detail that you can see. And in your algorithm, no matter which algorithm that you're using, you've got to say something to the and constrain the algorithm so it doesn't just go wild and put Mickey Mouses at smaller scales. You've got to constrain it and say, look, I believe anything smaller than this is just going to be a point source. It's just going to be, blank light. Or I assume everything smaller than this is going to be, let's say, I don't know, chicken shaped. And in the same way, you could assume fractals, smaller scale and larger scale, but there have to be a physical reason for that, right? At the moment, we just assume the simplest possible structure for the scales that we don't measure.
Sure. All right, the questions are getting heavier and heavier. Any more? If there are no more questions, and I'm going to, I think, wrap it up and say thank you very, very much for a fascinating talk, and we look forward to more in the future with new developments, and I'm sure very exciting developments. So yeah, and what time of the year do you sort of get to Hermanus? Is that in December? Or?
Yeah, usually in late December, mid-December, or early Jan.
All right, let's see if we can organize something sometime. All right, thanks very much. Right. Thanks everybody for attending. I've done a recording of this, so that will be available. I'll send you a link as well, Roger. All right, thanks very much.
Thanks for having me.
Superb. Thanks, everybody.
Sure. Cheers, everyone. Have a good evening.
Okay.
Thanks, that was really fascinating.